It's great to have Idan here. Idan is a new ideal postdoc. His main home is at UIC, but he's going to have a secondary home here at TTIC and with an office just right over there. So he'll be hanging out here some, and I guess he and Dravi live near each other and sometimes carpooling, which is great. So it's fantastic. Idan got his PhD in computer science under supervision of Arya Kazmilovich and Yishai Mansour. He works in machine learning theory, data-driven sequential decision-making, connections to game theory, optimization, statistics, private data analysis, causal inference, and information theory. And he recently received the ICML 2024 Best Paper Award. And it's so great to have him here.
Thanks for the introduction, Albert. So yeah, my name is Idan. I just joined Ideal. So this is like, thank you for the warm welcoming, TTI folks. It's really a pleasure. So this is just like roughly a type of projects I've been working on. It's like more like robustness, differential privacy, modern challenges in ML. We'll talk today about overparameterization. Beyond the worst case analysis, I really enjoyed the learning augmented algorithms program, machine learning theory, and like game theoretic landscape and learning. So feel free to look me up, let's chat and be active. So I will present a paper with Carolina, Madi, Roy, and Dan Roy. I was visiting Vector Institute as an intern, and we worked on this project, which is about stochastic convex optimization and applications to memorization, generalization, privacy. Some connections there. So feel free just to interact and comment and whatever you want. Okay, so let me start with the motivation of memorization and overfitting. So there is the known empirical evidence from 2014 where we can take a very complex model, completely overfit the training data, but somehow the test error is still small. We're able to generalize even though the test error is not zero. So definitely we're overfitting. There is a lot of noise in the training data, so we must memorize some outliers or like sort of irrelevant information in the training data. So when we overfit so badly, there must be some type of memorization. So this has been generalized in 2017 to many more data sets, and we see the same phenomena. Training accuracy is zero, and the test is not, but actually these are like good algorithms. And I want to mention that this is like probably not a new phenomenon. Like more than 20 years ago, these guys showed it also for like trees, for bagging, aggregating and boosting. You can see like if you have many classifiers, like the model is get more complex, the training error is zero, but the test keeps dropping. So perhaps it's not like a new phenomenon, but definitely got a lot of attention in deep learning. Which brings me to some considerations about privacy. Like if we memorize so many information about the training set, an adversary can come up with some inference attacks. It can just get to see the black box. It can come query the model in a black box way and infer which members were in the training set and which are not, which is like a major privacy leak. We can sometimes even reconstruct training data. So you can see like there are many images here that can be reconstructed. The images above are like the reconstruction of the original images. So you can see like it's pretty good reconstruction. And there is also this example by Carlini, where you can see that GPT can output very sensitive information about an individual, like phone number, address, and some stuff. And we can mitigate memorization by like using differentially private algorithms. But the question is memorization is somewhat like necessary for optimal error, or just we can come up with a different method that would still give like an optimal error, but avoid memorization. So this is the motivation of this talk. And it has been shown already theoretically that the answer is no. Like sometimes memorization is necessary for optimal error, which is by these lines. But this is our result. We'll explain why it is the same flavor but different. So what we show, like this is the main message, there is a price of overparameterization. We always say like, take many parameters and like more is better, more examples, more parameters, but there is a price for taking like many parameters. And the price is, you can give me any good learning algorithm with small XSL that is overparameterized, like there's many more parameters than training samples. The number of parameters should be larger than the number of training samples squared. And then I can come up with some simple instance and distributions such that there is a memorization of many samples in the training set. Okay. And I will define memorization, it's by like membership inference attack. Meaning there is an adversary that can identify many members in the training data. And if we have membership inference attack, we don't have privacy. So built in, there is some problem with the privacy of individuals in the training set. And we cannot prevent it. Sometimes it's like necessary. Overparameterization is necessary because if the number of parameters is smaller than the number of training samples, then we can have differentially private algorithms that mitigate memorization. And I want to say that this is not the only theoretical result in this flavor. Vitaly Feldman and these guys, they showed like they have a different learning model, and they showed that natural data sets are like have a long tail. And actually, when you have such distributions in real life, you must memorize in order to get an optimal error. So they define memorization in a different way, and their model is different, and they explore the distribution. We explore like the number of parameters, but I think it's like it's really connected. It's like of the same thing. So more overview of the results, like how we prove this theorem. So first of all, we show that any good learning algorithm must have strong correlation with the training data. We contain like large information about the training data. And we can translate this correlation to the training data to privacy attacks or memorization attacks. And there are some other implications where we can show that, so the information complexity we're going to explore in this talk is called conditional mutual information, but it doesn't really matter now. And we can show also that this framework is not optimal in SEO to obtain optimal generalization. And also there is no sample compression scheme in stochastic convex. So this is like roughly like the way we prove the result. Okay, so this is going to be the outline. Let me write it. So we're going to motivate SEO, and then memorization, differential privacy, generalization, CMI accuracy trade-off, and other applications. And prove ID. Okay, so this is the way I'm going to present it. Okay, so let's start with the usual model of learning from IID samples. There is an unknown distribution D. We draw random samples from a distribution. We give to the learning algorithm a training sample. It outputs a classifier for some function class. And the goal is to predict on unseen points, small error on random points from the distribution. And specifically in this talk, we're going to consider the beautiful model of stochastic convex optimization by a bunch of guys from TTI in the past and the present. And we're going to motivate why this is like an interesting model to start with. So what is stochastic convex optimization? The goal of the learner is to minimize population error. So D is an unknown distribution. W is parameters of a model. So there is a capital W convex set that is bounded, let's say by a constant. Z here is like a labeled sample. F is a loss function that is convex in the parameters and is Lipschitz, let's say constant Lipschitz. And this captures like very classic learning models, like logistic regression, SVM, and one layer neural network. So we don't know the distribution, we have an access to training data, and we have the empirical error, and we say that the learning algorithm is epsilon learner. If given some n of epsilon samples for any distribution D, it's the worst case, it has small excess error. So what is the excess error? It's the error of the learner in expectation, and we require this error to be compared to the optimal function in the class, optimal parameter in the class, up to some epsilon. And n of epsilon is called the sample complexity of the learning algorithm. Okay, so epsilon learner are going to be important. We investigate the properties of epsilon learners. Okay, why stochastic convex optimization, SCO, is a good case study for studying overparameterization. So first of all, it's a quite simple model, but already there are like many interesting phenomena happening in this model that don't happen, like for example in pack learning. So, for example, uniform convergence scales with the dimension. Like the empirical error of any, if I want to use ERM and I want to claim that there is uniform convergence, and the error, what you see is what you get. The error on the training set is close to the error on the distribution. This scales with the dimension. So if D is very large, this is not promising. Lately, it has been shown that there is actually a difference in this model, slight difference between ERM and uniform convergence, but it still scales with the dimension. Full batch gradient descent also scales with the dimension. But the interesting thing is that we can obtain generalization bounds that are independent of the dimension. So SGD, for example, I don't know if they proved it, but I think this is where it appeared first, SGD. And in the stochastic convex optimization paper, they showed that you can add regularization to an ERM, add stability to an algorithm, and the generalization scales without the dimension. Yeah.
That's one question. For the full batch gradient descent, what is in there? Is that a number of samples or a number of iterations? Because I think throughout here n is number of samples, right?
Yeah.
But I think if you don't care about number of iterations in gradient descent,
so I think it's like you should limit the number of iterations. Maybe.
That's I think that's number of iterations, not the number of samples. So it's not exactly comparable.
Yeah, I think it takes like n to be. Yeah, maybe probably you're right. Like you can make probably what you say is like you can make gradient descent dimension free.
The sample complexity of gradient descent, full batch gradient descent can have some full batch gradient descent. If you allow me to make some number of iterations that can maybe they don't have to be dependent on dimension, but they have to be quite a few, like a bit too many iterations, like quadratically too many, is I think achieves optimal sum.
So yeah, I agree. It's more nuanced. It depends how many iterations we allow the algorithm to run. Yes.
So, about the dimension-free rate, so what is the result exactly that you're referring to? Is it like, because when you say dimension-free, there could be hidden dimension dependence and like.
Okay, so where is the line here? So I'll tell you where is the. So the generalization is going to scale with two things. There is no free lunch. So there is the diameter. We assume that the parameters are like bounded in some convex set, and the F is Lipschitz. Let's say L Lipschitz. So I'm going to get something like that instead of D. So maybe what you say is that D is like.
Great. So unless you have some sparse structure in the problem, it's usually going to be.
So if R is small and L is small, somehow in the problem, convert to D, then you're going to get better.
Yeah, I agree with that, but it's not always dimension free. Sometimes, depends on the problem, right? But I agree.
No, I mean, in stochastic optimization, this is a known result. You can always get.
No, I agree with the result. I agree with this result. I'm just saying,
In other
for
models.
many problems, it scales almost.
Maybe, maybe. You're talking about stochastic optimization. Yeah. Sometimes you cannot avoid the dimension. That's what you mean. In other models.
No, I was saying RL versus D. RL versus D. Like, for instance,
So in some convex optimization problems, you say that like this should be related.
it's usually like, think of like linear regression in like some Hilbert space or something like that. Like, unless you make some strong assumptions on the tail of the spectrum, you cannot get liquid bounds. But anyways, I'm maybe regressing. I agree with what you're saying.
Okay. Let's chat about it. But I agree that there is something here. Like, maybe the dimension hides somewhere. That's what you see. Okay, so generalization is depending on the algorithm. Okay, like it's not like uniform impact. You can just run an ERM. What you see is what you get. You're going to be happy. Here it's more nuanced. Like the generalization depends on the algorithm. That's like what I'm trying. That's the point I'm trying to make in this slide. And let's just take a look at the zoo of learning model. So on the left-hand side, we have models that uniform convergence is equivalent to learnability, and we need the number of parameters to be smaller than the number of examples. And E, we have the deep ocean, we have deep learning, and SEO is somewhere like a step in the middle, where we can take number of parameters larger than the number of examples. And is a natural step to study overparameterization. We ask, like, okay, let's study memorization in stochastic convex. Okay. So this hopefully motivates SEO. Okay, so this is the way we're going to define memorization. Something called membership inference attack. And interestingly, it was like used similar definition by Carlini et al., like in empirical work about membership inference attack, and also by these guys from Differential Privacy. So we have the training sample S, and we have the learning algorithm. And now for every sample in the training set, we draw a first sample, Zi tilde. And let's say Z1I is the in sample point, and let's say Z0I is the out sample point. Then we flip a fair coin, Bi. We give it to the adversary. We give it the ZBII, like in or out sample, like randomly. Let's say the adversary knows the distribution, and let's say it gets to see the output of the model. Okay, and the adversary should guess if it was in sample point or out sample. How do we quantify if an adversary is good? Let's say the adversary plays this game for every sample in the training set. Yeah.
What is ZBI? I missed that.
So Z1I is the training sample, and Z0I is some random sample drawn from the distribution independently from the model, independent of everything. And we give the adversary one of these.
Oh,
And he needs to guess if it's like from the distribution out of sample or in the training set. Thanks. So how do we quantify if adversary is good? He plays the game for every round I, and we ask him to have low false positive rates, meaning with low probability the adversary will say yes on out of sample, but the adversary can say always no, and so we need to counter it with some true positive rates. So we say that the adversary like identifies or certifies the recall of M samples if it identifies m points that are in sample with some constant probability. The constant here doesn't really matter. It's okay. So this is the definition.
So are you deliberately considering a strong adversary which can access the distribution, or there is some application where it has access?
So sometimes the adversary can do less. For example, just the mean or approximation to the mean. I don't want to make any assumption on the distribution, so let's say it knows the distribution. But like in differential privacy, for example, the adversary can just have reference samples, or like, so you can have less. Like the adversary can have some other reference samples, approximate the mean somehow, and use it as a proxy. But I don't want to, so sometimes you can refine this. Okay, so is it clear? The definition is clear?
So I don't know if this is so important, but so what role does the index I play here? Like if the algorithm is symmetric, can I just completely ignore it, or like the adversary no I? Why do I need this to be for all I? Why can't I just check a single point?
So we can play this game for like we just want to say like how many like memorization entire across the training sample, not just one. You can play it with one round,
Right.
But we want to say like you play for each.
But for each one you play it separately. It's not that
Separately, yeah, it's separately, yeah. But the thing is that what we're going to prove is that there are enough pairs, such pairs, that the correlation is going to be large with the in sample and low correlation with the out sample. So the proof needs to take, like, you don't know which one are going to be in advance. Yeah, but you can quantify, if you want to do it with one sample, you can quantify like also this definition. And analyze it. Okay, I will. So this is the main definition. Take a look, see if you're okay with that. And it has been used. So, okay, main result. What we can show is that I can give like a natural instance of stochastic convex optimization and some universal strategy for the adversary, just testing correlations, such that if you give me an algorithm with small XSL, and the dimension is large, this is important, the dimension should be larger than squared, so it's a phenomenon of overparameterization. Then there's going to be a memorization of roughly 1 over epsilon squared samples. And what's interesting about 1 over epsilon squared, this is the optimal sample complexity of the model. So the learner is going to use 1 over epsilon squared sample, and there is like, and the memorization is going to be of like a fraction of the training set. So there are membership of many samples are going to be exposed, which is a very negative result. So yeah, specifically here, Xi is the soundness parameter of the adversary. We come up with an SEO problem. The loss function is just linear, and we can have an efficient adversary, such that if we have a learner, if we need optimal sample complexity, if any learner with optimal sample complexity, and the dimension is large enough, then we create scenarios where there is an adversary that is Xi sound. The false positive race is at most Xi, and the adversary can identify 1 over epsilon squared samples. Okay. So we can show it also if the loss is strongly convex. We can get 1 over epsilon memorization. By the way, it holds also for adversary that outputs a model like in the function class in capital W or out of constrained or unconstrained. So this phenomena holds in like many scenarios, and this is tight. Okay. This result is tight. So yeah, so overparameterization here is necessary. Otherwise, we have differentially private SEO algorithms for this problem.
And so in particular, this thing is very not differentially private. I mean, if someone can actually tell, some number of people, you're not supposed to tell anybody in the sample.
Yeah, so you can take like this result and then lower bound the epsilon parameter of privacy easily. Yeah. So it's a strong violation. This is like going to be the next slide. This is a very strong violation of differential privacy. And here even like you don't take like neighboring data set like adversarially. You just choose more points from the distribution. It's even weaker, and you can trace even more samples. So yeah, it's a very strong violation. And there is an interesting phase transition. Like either you have like a very strong notion of privacy, differential privacy, and then all of a sudden you lose privacy in a very strong sense. This is the point that.
This is maybe just a definitional issue, or maybe it has to do with how you'll construct a distribution. But shouldn't the SEO instance also be characterized by the distribution?
Mm-hmm.
Your SEO instance is just characterized by WZL. I would usually also characterize it with the distribution.
So I would say what is it? So what is the SEO? Is the loss function? Is the data space Z? But in SEO you want to prove for any distribution. So I don't consider it's a worst case model. So in SEO, you want to learn for any distribution. So if I want to show that, I want to come up with a counter example. Okay, this is the model.
Okay,
Makes sense?
Yeah, but still, this result is for every learner. You'll create a distribution.
Sure. Yeah. I'm gonna create some distribution such that if you're accurate, there is strong correlation with the training set.
So, but still, the distribution, which I kind of agree with Kshitij, I really think of it as the instance, but whatever, does depend on the learner. But if I understand correctly, the adversary does not know neither the learner nor the distribution.
The adversary doesn't know anything.
Nothing. It just sees the only thing it sees is the learn predictor.
Yes. Makes correlation tests if the distribution is such that this claim all is going to see.
And the other thing is I'm a bit confused about so. I mean the kind of lack of privacy here is 1 over epsilon squared. Like it's very small. So it's still like, kind of, if I want to learn very well, I learned a very small epsilon, I'm going to need like 1 over epsilon squared samples, but I'll also be able to actually be, I don't know if you consider it private or not, right? But like, I mean, there's going to be like only very few samples, very few points I might be able to identify. Am I understanding correctly?
So the amount of point is like small constant times 1 over epsilon squared. So imagine that C, I don't know, is like 10%.
Oh, this is not Oh, I see.
Samples.
This is the absolute number of samples.
Yeah.
I see.
It's not only one sample, it's like fraction of the training set.
I see.
And this depends.
So that means that if I really use, like if I'm optimal, then I'm basically, if I'm optimal sample complexity, then I can identify a constant fraction of this. Like,
yes.
Yes. Okay, I see. So that's very strong then, actually. Sorry, I thought it...
That's great.
Yes, that's very strong. Yeah.
And okay, so this constant, how we're going to control it, we can control it by this parameter, false positive rates. And actually we could quantify also this probability, and also like this is going to control here how many samples we can trace. And if we're okay with false positives, maybe we can increase that. If we're okay with low probability, we can increase that. So yeah, we can control it like with these parameters. So yeah, it's a very strong violation of rights.
I guess you probably couldn't hope to certify more samples because the learning algorithm could always, step 1, throw out all but and then go from there.
So this is why it's tight.
It's like the strongest you can hope for,
Adversary can always subsample 1 over epsilon squared,
right,
ignore the rest.
Yeah, exactly.
Sanity check. And this is actually how we prove that this is tight. Subsampling. Okay. Thank you for the questions. Makes everything much more clear. Okay, so let's be more clear about differential privacy. What is differential privacy? Let's say I have a database, dataset S, with users, and I have another neighbor dataset S prime, where I replace one member of the training set, the blue with the orange. And I give one of these datasets to the randomized algorithm. And the output on each of these databases as distribution is really, really close. If that's the case, then it doesn't matter which adversary is going to observe this output. It cannot infer like if the blue or the orange guy were in the training set. So we pretend any member of the training set. Well-established notion of privacy, very rigorous. very nice properties. So formally, if you want the formal definition, the algorithm is alpha beta differentially private if for any neighbor data sets that differ in one data point. For all events in the output range of the distribution, the probability of this event is roughly the probability of this event up to e to the alpha multiplicative error and beta additive error. And what is differentially private SEO? I require the algorithm to satisfy privacy, but also to get small XSL at the same time. So it's an extra requirement from the learning algorithm.
So you need to change your generalization error definition, right? Because your algorithm is randomized now. I think in the original definition there was no randomness over A.
If the algorithm is not random, you cannot achieve privacy.
Right, so just small. In your original definition there was only randomness over sampling of S and not A. But now WS can be random. Even S.
The WS is random. There are coins that are not coming from the distribution. That's what you say. It's random coin by the algorithm, and it's necessary. Adding some noise. True. So it's like independent noise that the algorithm uses. Sure. Good. Thank you. Okay. So very nice result by these guys, Vasily, Feldman, Talwar, and Akurta. They showed the optimal differentially private SEO convergence rate, and it's as the following form. And what you can see, this is the optimal. So they showed already that t is larger than n squared, that we don't have differential privacy. So this was known prior to us. But as Avrim said, what we show is much stronger. We show that there is a much stronger violation of privacy, which we call memorization. So this was known, but this adds, makes the statement much more strong, I think. And also, this is not like we studied in in the context of stochastic convex optimization. This phenomena of memorization and tracing is known in the privacy literature for mean estimation. So they already showed these guys, Pan, Ullman, Hans, and these guys. They showed already that if the dimension is larger than n squared, there is this phenomenon of membership inference attack tracing. But the thing is that we show it for algorithms in the learning model, and they showed it for private mean estimation. And what's hidden in all of these results is something called fingerprinting lemma that I think it's very useful, and we're going to talk about. Okay, so this is their graph, and the square root of t. There exists a differential privacy, and here we show that there is memorization. So there is a phase transition. So yeah, maybe if we have a different notion of privacy, the picture is different. For example. Okay. So I think I'm gonna shift for a different. So I think this is probably, if I could say, this is the main part. If you want to discuss, this is a good time.
Isn't membership attack strictly harder than differential privacy? How do you see that?
So what we can show here that actually no, there is no room here for improvement almost. You move from differential privacy to memorization. So what you're asking, maybe there is a different notion of privacy, maybe, where this phase transition is different. Either you have privacy, strong sense, or you lose privacy completely. Is that the question?
So does membership attack imply differential privacy?
Yeah. This is, yeah. So membership attack, yeah, every master is also easily implies no DP. We can lower bound the parameters of differential privacy with the parameters of the memorization algorithm.
Is this easy to see from the definition?
Not very complicated. If you should guess, that's what you'd be your guess, and it's not very difficult to show.
I think my thing is I think I know the answer, but does the other implication hold? Like, you're showing here that, they showed that there's no DP, you're saying, okay, there's also no membership attack.
Mm-hmm.
Is it always the case, actually, that if there's no DP, there's no membership attack? Or in principle, is a membership attack a stronger notion? Are there other cases, not in SEO, where you have
so in
where,
LP, the answer is in LP SEO, even not in this is L2 SEO. We analyze now LP SEO, and also there is the same phenomena. So this is a great question to show like where other models, where there's actually a difference. That's what you asked. Like there is not this.
Even in synthetic, in principle, if you just look at the definitions, right? Is it just always the case that?
Yeah, it's a good question. I don't know.
So I think you should be able to construct.
I think because your notion of membership attack, the attacker doesn't know the data, only knows the distribution.
Yes.
Right. Whereas differential privacy requires to be private, even if the attacker knows everybody else but you.
Right.
So, for example, suppose we took the parity of all of our salaries or something. Like that's not differentially private because somebody who knows everyone's but yours gets yours.
Right.
But I think from a distributional perspective, there's no way to tell. So I think in principle, they're separate.
Yeah. Or I think if you leak very little, like if you leak a tiny bit of information about each one, kind of depends on the rest.
So the conclusion is that sometimes there's different phenomena. This is the conclusion.
You could have situations where you're not differentially private, and yet you can't do a membership attack.
Yeah, So it's really is a strictly stronger notion. Like it's not that you just always, whenever you have no DP, it implies.
Not in SEO, probably. Suppose I should guess that this is a strictly. That's what I would guess also.
Yeah. So that's
interesting.
So would you speak about your distribution, like how you construct the distribution for the learner, or?
So I'm gonna hide it behind something called fingerprinting lemma, and not even the simpler one, like something much more complicated. So that the proof is pretty messy. I'm gonna give you the flavor of I'm gonna give you the simple fingerprinting lemma, and then I will tell you that this wasn't good enough. We needed to work quite hard to create a different fingerprinting lemma. And actually, John Ullman came up with a different fingerprinting lemma, even simpler than ours, that allowed us to prove. But yeah, I'm gonna show you where I hide it, and then we can discuss it. So the whole game is going to be about creating a distribution such that if your estimation is accurate, you have large correlation with the training set. This is the game, how to construct them. And also, this is not going to be constructive. We're going to draw some prior, and we're going to say there exists a distribution.
I see.
It's not going to be even explicit.
So it's not going to be clear whether it's a natural distribution or not. It's not going to be obvious at least.
No, it's going to be pretty natural. No, the distribution is going to be natural, but I'm going to show you the existence. The distribution is going to be natural. Can be just Bernoulli, where I draw the parameter from some uniform distribution. So the distribution is natural, but I don't know usually an existence. Okay. So now I want to tell you about the tools that allow us to prove the result and also connect it to generalization. So what is generalization error? It's the difference between the true error of a model compared to the empirical error. And usually the way we bound the excess error is by the optimization error and generalization error. So we want to minimize the loss on the training set. At the same time, we want to have generalization. So this is generalization. And there are many techniques to prove generalization. So we have uniform convergence, which is a property of a function class and not an algorithm. So what you see is what you get for any model in the function class, every function in the function class. We have a stronger notion, like we have stability, that if we change one input in the training set, it doesn't change much the output of the algorithm, and there are multiple types of stability. Uniform stability is the strongest one, but this is a property of an algorithm. That's the point. Sample compression is also a property of an algorithm, where if the algorithm can only pick a subset of the training set and output a good model, this is also give us like a generalization that is not uniform convergence, not use uniform convergence. And okay, so I want to focus on like information theoretic methods, which says that I can bound generalization by some information complexity between the model and the training set. So the natural candidate for such an information is what was suggested by Shu and Raginsky, is the mutual information between the input, between the model and the training set. Okay, so this is very natural, but however, it doesn't like capture the optimal generalization. So in PAC learning, I didn't define, but in PAC learning, there are classes that are learnable, but this input-output information can be unbounded. So it gives us only one side of if the only if of the generalization statement. And also lately, Wai showed that also in SEO, this should grow with D. So this is a natural try, but it fails sometimes. So I want to define what Thomas Steining can.
Sorry, can you go back to the previous slide? So just the quantifiers here. Are you so in supervised classification? You're saying the classes. So that's exactly my. So thresholds where for any learning algorithm, there
is a distribution such that
the mutual information is high.
Unbounded. Some kind of precision issue, I think.
Okay, I mean, I'm actually curious to talk about that later, but I mean, because my understanding of quantifiers are a little bit different. But yeah, I mean, I'd be interested to talk about that.
So yeah, there are two results about that.
Oh, maybe I'm thinking only of the first one. Okay.
So Lydia Zacchintino and Thomas Steiger were able to come up with some interesting different notion. So now, let's say I have a super sample of 2 n samples drawn from the distribution. And now I choose uniformly, let's say I divide them to pairs, and I choose uniformly one of each pair. Okay? And then the chosen one is going to go to the training set. The non-chosen ones, like ghost samples, are like just for like exercise. They're not in reality. And the algorithm gets to see this training sample. And now the conditional mutual information is the mutual information between the output of the model and this membership vector condition on the super sample. Okay. So this is some. They try to normalize sort of the information. And the cool thing is that you can upper bound the generalization with this notion. And actually in PAC learning, it fixes the problem. Like you can get near optimal bounds with this notion. Okay, so in PAC learning is strictly stronger. So we actually asked what about SEO? You can see from the nature of the CMI is like really similar to the memorization game we defined. There is a reason for that. So we were able to connect the CMI to the definition of memorization that people actually used. Okay, so this information notion was useful in other models. So yeah, so the difference between CMI and input-output mutual information. Let me repeat Thomas' words. The difference is like instead of trying to come up with a sketch of a criminal, OI gives you a lineup and you need to say, okay, this is the criminal. I like this example. I think everyone can imagine this. Yeah. I don't know how to draw a sketch. Show me the person. Maybe I will. This is more philosophical explanation. Okay, so the main tool behind our results is a trade-off of the CMI, this information notion, and accuracy. And we showed that, like, if you have a good learning algorithm and that is overparameterized in high dimension, I can create a distribution such that this CMI is large. Okay, so it's the same flavor. Here I can have any n that is larger than the sample complexity, as opposed to the previous statement, and the CMI is going to be lower bounded by 1 over epsilon squared. Similar results for strongly convex losses, 1 over epsilon, and it doesn't matter if the learner is like proper, constrained, or improper. Like, same phenomena. So like CMI is like information, like I chose to present the memorization result first because I think it's more intuitive. This is like more technical, but actually we use this idea to construct the memorization. Okay, so this is the.
This result would imply the previous representation.
Hmm?
This result implies the previous result. This is like more fundamental.
You like use this lower bound to construct the memorization. Yeah. Okay, so one implication to generalization bound in the stochastic convex optimization. What we can get from this bound is this convergence rate, and if we know that n roughly 1 over epsilon squared is the right sample complexity, but somehow we cannot see it from this bound. So this bound is sometimes vacuous. So what we can see from this bound is actually you can get dimension independent bound from the CMI, but it's not going to be 1 over square root of n. It's going to be 1 over n to the. So it's better than input-output information, but it's still not optimal.
So is this? It is, but I'm checking this. Is this from then? Is for SEO the best bound you can get with CMI for any method is 1 over.
Yeah.
Is it 1 over epsilon to the 4th?
Yeah. Correct. So previously it would have been shown by like for a specific algorithm, but by these guys for gradient methods. But actually it's like for every like learning algorithm. Okay, so this is a limitation of the CMI framework. Also, we can show that sample. Okay, so what is sample compression scheme? Let's think about SVM. We can always take the support vectors, use them to output, throw away the rest of the samples, and use them to get an optimal classifier. So this is a definition of sample compression. And in PAC learning, we know that we can get like a constant size Shine1 and Amir Yodai. I've showed that you can get like VC times 2 to the VC compression that is independent of the rest. We showed that in SEO, this is the best you can get. So the sample compression is going to scale with the accuracy. So this is another implication. I want to elaborate. Yeah, this is more important. So what are fingerprinting codes? A very cool object, combinatorial object, that originated, I think, in crypto. And what they tried to do, they tried content companies, let's say they want to protect their content, so they want to implant some watermarks such that if some malicious user would like to distribute the content, they will be able to trace him back and say, okay, this is you, we're banning you from using Netflix forever or something. So yeah, so this is so you can see the tracing phenomena. Yeah, they want to trace users for doing something illegal. So then a very nice paper in 2014 by Idan, and they showed that actually you can use this idea to lower bound private estimation. So you can very cleverly they show that fingerprinting codes are going to control a trade-off between accuracy of a model and correlation with the sample. And as a result, they improve tight lower bounds for mean estimation. So I think this connection wasn't known before. So what is the, so okay, I think one of the messages I want to make today is that fingerprinting is an interesting object. Like we should be aware of it, not only in privacy, not only in like crypto. It's super fundamental. Like it says that if you have high accuracy estimator, there's going to be correlation with the training samples. High correlation can be used to tracing, violation of privacy. Like this is very intuitive, but it's quantified, for example, by this. This is, I think, the simplest fingerprinting lemma. So it has been used quite a lot since 2014 in the privacy community. What it says. So it's, let's say I have an estimate, or like I have a function that is an estimator for some unknown mean. And then what I do, I draw draw mu from uniform distribution on like some interval, and then I draw sample from some distribution that is parameterized by this mu. And then what the claim says is that this is the entire correlation of the estimator. Think about the estimator to be, I don't know, just the average, okay? So this is the correlation of the estimator f of x with all the training samples. So this is a correlation with one sample. And this is like the mean squared error. So when you sum them, they are like larger than some constant, meaning if someone is higher, the other is lower. Okay, so they balance each other. If you want to get a better accuracy, the correlation should go higher. So this is one dimension. They're able to construct also like the distribution in higher dimensions using the product distribution. And lately, in 2023, they were able to show even for non-product distribution. And so I think it's a very cool object and very useful that you should be aware of. So yeah, very high level. This proof is quite messy, but I want to give you like the flavor of sort of what's going on. So I'm not going to tell you the right fingerprinting lemma. I'll show you where I lie. So the parameter space is going to be just the ball, radius 1. The data space is going to be a normalized cube. A loss function is going to be this linear loss function. Remember the definition of this CMI. Okay. And then I define these two correlations. One correlation with the Z1I and correlation with the Z0I. So one of them is going to be chosen to be in sample and one out of sample. Okay, so here there is some scaling metrics, and there is this mu. They're coming from some like clever fingerprinting lemma. So I don't want to make it more messy. But basically, what it says, like, what I want to do, I want to say, okay, sometimes one of them is low and one of them is high. And then an adversary can distinguish which one was in sample and which was out of sample. It's like, I think, quite intuitive. So in order to make so UI bar is like the one that wasn't chosen to be in the sum. We can show that if the dimension is large, this random variable is upper bounded by epsilon over n. So this is where we're going to use this condition. And then we define a set for which like there is a look at pairs, like one of these two pairs, that one of them has large correlation, larger than this threshold epsilon over n, and one is lower. Okay? So intuitively, this set is like the points for which adversary can observe one of them and say, I'm going to test. If it's larger than epsilon over n, I'm going to say yes, and otherwise I'm going to say no. Okay? And then by using many calculations and information theory, Fano inequality and some other things, we can lower bound the CMI by the expected number of these points. And then we can lower bound this object by the sum of correlations squared divided by the sum of squared correlations. And here there are like many technical details, but to lower bound the denominator, we use some refined fingerprinting lemma. What is more refined about it? Also, first of all, the uniform distribution should scale with epsilon. We needed some higher variance, and it seems like we couldn't avoid it. And also, we needed like this scaling matrix that I don't show you here, but it's like very not clean. So there was so with the usual fingerprinting lemma, we could show like 1 over epsilon. But we couldn't like avoid the complication, and then John Ullman, I think, came up with a more clever idea. Just instead of uniform, generalized uniform with a better distribution, this should work. So we here I'm hiding like a lower bound on this object by a fingerprinting lemma, And this guy upper bounded by some concentration results, but I don't want to make it more complicated. So hopefully I could make, like, the claim is simple. Like, if the dimension is high, out of sample the correlation is going to be low. In sample the correlation is going to be high for sufficiently for 1 over epsilon squared pairs. And this is the idea. 2 minutes. What is the adversary strategy? The adversary could just check if what I gave him, he will come up with, let's say, with A, and he will check if the correlation is large enough. If yes, he's going to say yes, otherwise he's going to say no. Okay, follow-up works. This helps us to prove even stronger lower bounds for LPSCO. We're writing it currently. And actually, this notion of tracing, we can generalize it and lower bound not just like memorization and privacy, also like more classic stuff, generalization. We think that there are like much more applications to this tracing property. And yeah, takeaways. Good learning algorithm must sometimes have large amount of correlation, leads to memorization, lack of privacy. As a result, CMI has some limitations. Future work, I think there are many ideas for future work. Okay, we studied SEO. Let's go beyond SEO. Reconstruction attacks. We were able to do like membership inference attack, what we couldn't reconstruct. There is some struggle there. Maybe other notion of, okay, so what Avim and Nadi said, separate these two notions of memorization and privacy. And maybe other notion of privacy that makes sense in this context to mitigate memorization. And fingerprinting, be aware of this simple idea. In powerful tool, also called like Stein's lemma, if you want to look for it. It was discovered in statistics like long time ago. So I think this is be aware of this hammer. Okay. Thanks.